In this last lecture of the series about bases, we are going to focus again on this relation and the last animation we kept V fixed and moved Q, R and S in order to see how the coefficient of the linear combination would change. Admittedly, the choice of Q, R and S had to be well chosen, because otherwise there are certain degenerations that might occur. First of all, if we just let Q, R and S vary randomly, it might happen that at some point the vectors will be linearly dependent one to the other. So there might be one of these three vectors which is going to be a linear combination on the other two, making the three vectors no longer linearly independent, and therefore making them no longer generators of R3. So in that case, V might not be in the vector space generated by the two independent vectors. So this is one of the possible critical cases that may happen. The other critical case is when V becomes linear combination of just two of these vectors, for example Q and R. So in that case, the parallelepiped become kind of very squeezed up very much and looks like a parallelogram. So it kind of loses one dimension and becomes flat, becomes similar to some polygon embedded in a plane. So we can see both of them in the following animation. I will stop and comment when the three vectors will tend to be linear dependent while moving randomly in different paths, and then also it will happen that V will become a linear combination of just two of these vectors. So we never really reach exactly that behavior, because all the animation is generated by assigning numbers, random numbers to these vectors. So it is almost impossible that they become exactly linearly dependent. So that would be a singular behavior, and it would not be possible to find a linear combination. But we can actually see when this is about to happen, so they are almost linearly dependent, but not exactly linearly dependent, we can see what happens to these coefficients. There is a very peculiar behavior that will be apparent. So we will never actually simulate the exact linear dependence, because in that case V likely not be in the vector space generated anymore. Therefore, this equation will not have any solution for K1, K2 and K3. But as we approach to that situation, we will see a very strange behavior from the geometrical point of view. So let's see. This video will show the movements that these three vectors will do in a certain time frame without any construction decomposing V as a linear combination of these Q, S and R. Just to show, just to highlight the movements of these three vectors in the following animation. Okay, so you see they will be doing exactly this path after having seen the different choice of vectors that will happen in the next few seconds. Now we go back to the final situation in which we ended up the previous lecture. So we had a vector V, and we had this very same choice of vectors q, r, and s. Now they will be making a different movements from the one we have seen in the previous lecture. These movements are more random than the previous ones. The previous ones have been selected in a particular way in order to not to have any degeneration in the expression of the linear combination. These ones are much more randomly chosen, so that we can see what happens if no particular choice of the vectors is being made. So we will have to recess the point of view for a reason that will become clear later. But while we will recess the point of view, the vectors s, q, and r will be moving, while the vector v will remain fixed. Okay, so now we are far enough to see what's gonna happen in the first critical situation that we will encounter. Okay, so clearly there is something strange going on in here, and this is the result of the fact that we are getting very close to the situation in which the three vectors become linearly dependent. Okay, so in that case v is not going to be in the vector space generated by the three vectors, and this is being reflected by the coefficients in the linear combination to explode. So the fact that these parallelepiped have these edges so long reflects the fact that the coefficients of the linear combination are become, some of them at least, are becoming really huge. And for the theory that we have done so far, this is very much ununderstandable. So why, as the three vectors become more and more linearly dependent, the coefficients of the linear combination would explode this way is not clear at all, but it will become more clear in the next lectures. So let's continue and see the next critical situation. Here we go. So this is the next critical situation. So you see the parallelepiped becomes a parallelogram, then can be embedded in a plane in a sense, and this corresponds to the fact that v is going to be a linear combination of just two of the three vectors, and the component, the coefficient of the third vector tends to be 0. Okay, so in that particular case we'll have a situation that recalls like a two-dimensional situation like this. Okay, so now we are getting more and more away from critical situations, and the parallelepiped becomes more classical in its shape and three-dimensional. Okay, so this is the final frame, and we see that the coefficient of the linear combination are quite well in their 3 or 4 units. So we have 4 here, we have 3 here, and I cannot read what's underneath the xy plane, but so this is a more typical situation that is very far away from a critical position of the vectors q, r, and s.